Okay, so looking at this problem, I see we are looking at a closed rectangular box that is made up of two kinds of materials. Okay, so, and then they're going to say that it has to have a capacity of 4 cubic feet. So therefore, we know they're talking about volume, which you correctly identify as length times width times height. Perfect. Okay. Um, so I'm not quite sure where we're getting to there, but maybe I'll figure it out as we go along. But that equation is not jumping out at me at the moment. So now the next thing, they're saying it's made out of materials. So what we're really getting at is surface area. So if you were to think about the box, this is kind of just like the picture from number 11. It's just a box that's going to have some length, some width, some height. It's going to take a piece of cardboard or a piece of metal or whatever this is to make, there we go, cardboard and cardboard, light and heavy cardboard. So it's going to take some pieces of cardboard or metal, or sorry, lightweight cardboard or heavy cardboard to make this box. Now they're telling us they cost different amounts. Oh, I apologize. Let me backtrack for just a second. We know that the volume has to be 4 feet. So instead of doing volume, I'm just going to say we know that length times width times height has to equal 4, but always give it units just in case they don't match later. We know to match them up here. Okay, so 4 cubic feet. Now, okay, back to what I was saying. We're going to make this box. So they're telling us the sides are made with a lightweight cardboard that is 13 cents per square foot. So this side right here, how many square feet is that? Well, that's just the area of a square. How do I find the area of a square? Well, length times width, or in this case it happens to be another height. So this face of the box, kind of this front side, is going to come from length times height. Now you can imagine we have another one of those here on the back of the box that's going to have the same dimensions. That back side is going to be, again, be length and height. So we need not one of those, but we need 2 of those. Right? Now, those are going to cost us, the sides are made with 13 cents per square foot, so whatever this square footage is that we get from doing the length times the height, we just need to take that, and then we need to take that and multiply by 13 cents. So this will be the cost of that face, the front and the back faces of the box. Now, that's not going to be our total cost though, because we're going to have more costs. We now have the other sides over here, this side and this side over there. Those 2 sides are going to be made from a width and a height. So we need to do a width and a height, and since there's 2 of them, we need 2. And the cost of those, again, is going to be the same, 13 cents. So that's going to be the cost of the sides of the box. Now, for the top and the bottom, this is the expensive part. We need a more heavy-duty type of material for the top and the bottom of the box. So, there we go, top and bottom. So, the math is still the same though. We still think of it the same way. The surface area is going to be length times width. We need 2 of those. And then instead of costing us 13 cents per square foot, this one's going to cost us 52 cents. So 0.52. Okay, so now is there anything else that goes into the cost of the box? That looks like it. So now the question is just saying, what should the dimensions be if the cost is to be minimized? Well, so now we proceed kind of with our normal stuff from the section. We have to minimize. How do you minimize a multivariable equation? Well, we take partial derivatives. So the cost is a function of length, width, and height, but notice we have a subject to. We're also subject to a constraint. We know that length, width, and height has to equal 4 feet. So when we are subject to, we have 2 methods. We can either go Lagrange, if I spelled that right, or we can go substitution. My rule of thumb, always substitution unless unless you can't. Always try substitution first. So I'm going to go ahead and divide by width and height. So that to me gives me length is equal to 4 divided by width and height. So everywhere I have a length, I'm going to replace it with 4 divided by width height, and I'm going to simplify this math a little bit. So 2 times 0.13 would just be 0.26. So I'm going to try substitution. So here we go. Let's hope it works out. Cost is equal to 0.26. That's just the 13 times 2. Now I'm going to substitute the length with 4 divided by width height times height plus 0.26. That's, you say 2, but you write 3, Professor Dwork. Not good. Okay, there we go. 0.26. There is no length in here, so we leave that alone. Plus 0.52 times 2, 52 times 2, so that'd be 104, $1.04, times length again gets substituted by 4 divided by width height times width. Now we can do a little bit of simplification to make our life easier. The height will divide with the height, the width will divide with the width. Once we do that, so now you can see it cleans up a little bit easier. Now we just have this equation here, and we can again simplify a little bit if you want to. 4 times 0.26, so that's going to end up being $1.04 divided by W plus 0.26 WH plus, now we have $1.04 times 4, so that's going to be $4.16 divided by H. There we go. So now we're ready. We've substituted in. By doing the substitution, we have now guaranteed that whatever equation we come up with here, it will satisfy both our original cost equation and it will satisfy our constraint. So we can use our partial derivatives, the derivative of the cost, changing cost with respect to width, and then we're also going to do the changing cost with respect to height. And once we know those, we can use those to back solve and for the length, and we'll have all of our dimensions. Let me know if you need more, but that's the general setup, and if you can do the rest of the assignment. At this point now we're just in the algorithm.